In this video series, we will talk about mathematical physics. I often begin my videos with an overview slide, which I spend 4 or 5 minutes at the beginning of my videos going over. And the reason why I like this overview slide is one, I think it's a good start for a crib sheet for studying for exams. Two, I find it really useful, a useful exercise to try to condense my most important points onto one page, hopefully. Sometimes I go to 2, but I really try to condense everything to one page. 3, I also like the fact that when I can condense my main points into one sheet, I feel like that the material must be manageable after all. It all fits on one sheet. Admittedly, though, sometimes my one sheet of paper is actually quite full. So this is what I consider a very reasonable one-page condensation of the unit. With that introduction to this video series, I will start with our first video, which is to review vector and matrix algebra using Einstein notation. Here is my overview sheet, which we will spend 4 or 5 minutes going over, and then we'll go over each topic in more detail and with more examples. So first, just because this is kind of a physics sort of math class, we have a little bit difference in symbol. So I have this table here to show that a lowercase letter represents real numbers. An uppercase letter with a line drawn underneath is a complex number. Our uppercase letter with a subscript is a vector component, whereas a matrix or tensor element is an uppercase letter with indices. For the entire matrix, we take the uppercase letter and put it between brackets. Our symbol for a vector is an uppercase letter with a bar over it. We have e to the I with a little hat for our basis vector. An uppercase letter with 2 bars over it is a tensor, and a script L will be an operator. With this, a 3-dimensional vector v bar can be expressed as v subscript x. So that's the x component using this notation here, the capital with the subscript. So v to the x times the x basis vector plus v to the y times the y basis vector plus v to the z times the z basis vector, which then if we substitute 1, 2, and 3 for x, y, and z can be written in summation form as v to the I, e to the I hat. We can further condense this notation here by using Einstein's summation convention, which assumes a summation anytime a subscript is repeated in the same term. So for example here, instead of having the summation v to the I, e to the I, since the I appears twice in the same term, we can condense that simply to v to the I, e to the I. Then it's understood that this is a summation. Indices that are summed over can be replaced with any other index with the same range of values that is not already in the expression. So in other words, if I goes from 1 to 3, if j also goes from 1 to 3, we could just replace these i's with j. So this could be v to the j, e to the j. And also for this example, a sub ij, b to the j, we can replace the j. Again, here the j is repeated once, so this is summation is understood, so I can replace the j with r if we like. Indices that appear only once cannot be replaced in this way, so this I over here cannot just be replaced with k, for example. And we will discuss why that is when we go into the subject with more detail. We will use the summation convention to look at matrix multiplication, and also not on this overview, but we will look at matrix rotations. Then we will continue with the dot product using this notation here. And with that, we will look at the Kronecker Delta function, this delta sub ij. And then last, finally, we'll look at the cross product using summation notation. We will also need to define this Levi-Cevita term. And we have a couple of important properties of the Levi-Cevita as well. So that's our overview. So now we'll back up, go through each topic in more detail and with more examples. First, we have this table of different symbols and notations, which is quite different than what I am used to in seeing in a math class, because we used to have lowercase as vectors and uppercase of matrices, but because this is physics, we need a different set of symbols. So first, our lowercase, those denote real numbers. Our uppercase with the bar underneath will denote a complex number. Our vector component is a sub I, and our vectors are going to be this capital A with a bar over it. Its components are a sub I. A matrix then is m sub I dot to j, that's a matrix or tensor element, and a matrix itself is denoted with brackets around the capital letter. We have our basis vectors, either the I hat, which might be familiar from vector calculus. We have a tensor, which is a capital letter with 2 bars on top. We'll talk about tensors in a future video. And then we have the script L to be an operator. And when I was first learning this new notation, I just put it all on a sticky note and I just put it on whatever page I was working at until finally I got used to this new notation. So with this, a 3-dimensional vector v, again our vector is an uppercase with the bar over it, can be expressed as v of x. Remember, this capital letter with a subscript is a vector component, so this is the x component in the x direction, and our e sub I, those are our basis vector, plus v sub y, that's the y component, times our y basis vector, plus v sub v, z, times our z basis vector. And then if we replace this x, y, and z with 1, 2, 3, we can get this subscript notation that our vector v now can equal to v1, e1, v2, e2, and v3, e3. And then written in summation notation, we put the sum I equal 1 to 3, v sub I, e to the I. And a quick note, Cartesian basis vectors, which is what we're going to be working with in our first chapter here, so our Cartesian coordinate system x, y, and z, are orthonormal and position independent. Orthonormal means they are unit length and perpendicular to each other. So the e basis vector, the y basis vector, and z basis vector, they all have length 1, and x and y are perpendicular, y and z are perpendicular, and x and z are perpendicular. Position independent means the basis vectors do not change their orientations as we move around in space. So I'll look forward to seeing basis vectors that do change their orientation as we move around in space, because you physics guys had some weird stuff going on. So here I have our symbols, and I just moved that note about our 3-dimensional vector can be expressed in the summation notation over here. And now we'll look at our Einstein summation convention, and that is we're going to assume a summation anytime a subscript is repeated in the same term. So in other words, here our summation of I equal 1, 2, 3 of v sub I, e sub I will equal to v sub I, e sub I. So because the I is repeated in the same term, we assume that we're summing over the limits of I. The combination of subscript and summation notation is referred to as subscript/summation notation. We'll do a couple of more terms and then some examples. A dummy index is one that is repeated twice in a single term and is summed over. So for example, this I here is repeated twice in the same term, and so we will sum over it. I have this written out. I have my v sub I, e sub I here, my dummy index. It's repeated twice in the same term, so I sum over. And in physics, we assume we are working generally in 3 dimensions, so I is going to go from 1, 2, and 3. So we have v1, e1, plus v2, e2, plus v3, e3. So for our dummy indices that are summed over, they can be replaced with any other index not already in the expression with the same range of values. So if j also goes from 1 to 3, and j is not already in this expression, because you don't want to mess up, reuse an indice if it's already there. So if j is not already in the expression, we can replace I with j, and that's just fine. So here, because once we expand our summation, you can see that j goes away. So this will come in handy when later we want to do some simplification of expressions. You can change your dummy indices to a different indice, and that'll be just fine. In contrast to a dummy indice, a free index occurs only once in the expression and cannot be replaced by another free index. Another example, if we have a sub I, j, b sub j, so here I appears only once, so it is a free index, whereas j appears twice, so it is a dummy index. So we're going to sum over the dummy index, and we'll get a sub I, j, b sub j is equal to a sub I, 1, b1, plus a sub I, 2, b2, plus a sub I, 3, b3. And as I mentioned, we can call this j, we can replace j with some other index like r, and so we have AIR, BR, so now we can sum over R if R goes from 1 to 3, and you see we will get the same expression. Here is our last example for now. So we have a sub I, j, b sub j, plus a sub j, I, b sub j. So j appears twice in this first term and twice in the second term. Remember, terms are things that you add together, so there are two terms in this expression. So j is a dummy variable, and I appears once in the first term and once in the second term, so I is a free variable. So again, when you're looking over subscripts that are repeated in the same term, you're not looking at I repeated in the same expression, it's in the terms. So I is free, so a sub ij, b sub j plus a sub j, I, bj is equal to, first we expand our summation over j, so a sub I1, b1 plus a sub I2, b2 plus a sub I3, b3. I had to make a little correction here, so this is a sub I3, b3, plus now we expand over j, so a sub j equals 1, I, b1, here j equals 2, a sub 2i, b2 plus a sub 3i, b3. I have my summary of Einstein summation over here, so I could add one more note. So when we write equations, when we just talk about vectors like c bar equals a bar plus b bar, this does not depend on a choice of coordinate system. However, when we then go and talk about components, our c1 and our a1 plus b1 and c2 equals a2 plus b2 and c3 equals a3 plus b3, at this point, the c1, c2, c3, these are coordinates in a coordinate system. So our results written in subscript summation notation, right, because it has a subscript I, we're talking about these coordinates, they're tied to a particular coordinate system. For this reason, we will convert final results back to vector notation like this whenever possible. Next, we're going to do matrix multiplication. That is, the matrix M times the matrix N is equal to the matrix P. And in subscript summation notation, we have M sub ij, N sub jk is equal to P sub ik. We are going to derive this formula, but when you're working with subscript summation notation, you don't want to derive the whole formula every single time. You want to remember this, but this isn't too hard to remember because it's very familiar. If you have I rows and j columns, to make the multiplication, matrix multiplication work, you have to have this matching. This has to be j rows and k columns, right? So these two inner indices have to match, and then what they do is give you a matrix of size I, k. So that's exactly what this formula here captures. So as I mentioned, we are going to do some derivations with this formula, but this is a formula you do want to remember. So we have P is equal to M times N, and we wrote out the matrix P, a 3 by 3, times M times N. Now to get the first row, first column of P, if you recall, you're going to multiply the first row of M times the first column of N. So basically, to get the ith j element of P, ij, you're going to multiply the ith row of M times the jth column of N. So for example, if you're looking for P21, that's the second row, first column element of P. So I equals 2, j equals 1. You're going to multiply, this is second row, the second row of M times the first column of N. So here's the first row of M times the first column. So you have M21, N11, M22, N21, M23, N31. So what you look at when you're looking at the row, you're going to hold the I element constant at 2 for the second row, and you're going to let j go from 1 to 3. Whereas in n, you're going to let the row go from 1 to 3, and you're going to hold the column at 1. Generalizing from P sub 2, 1, so P sub ik, to get the ith row, kth column of P, in this case we were getting 2, 1, but now ik, that's m sub ij n sub jk. That is, we multiply the ith row times the kth column, and we let j range over the index 1 and 3. So when we did 2, 1, right, we set ith row, jth column was set, and our j indice ranged. So when we expand this using Einstein notation, what we get is I1 n 1k plus mi2 n 2k plus mi3 n 3k. And you notice, once we expand over or sum over j, the j index disappears. So summing over the index is often called contracting over an index because we get rid of that index. And one of the things you want to be careful of is because matrix notation lacks a mechanism for keeping track of the geometry of the coordinate system. So for example, when you have a vector v and you spell out the basis vectors e1, e2, e3, that is the vector. However, once you write in coordinates 1, 3, 2, you've lost, you haven't kept track of the bases. So we use this arrow here instead of an equal sign because the arrow implies that v, this vector v, can represent, or I'm sorry, this vector v can represent our vector v, and that calculations can be formed using it, but we must be careful not to directly substitute one for the other without specifying the basis vectors associated with the components of v, this side. Next, we're going to look at vector operations, and we'll start with the transpose operation and a rotation operation. Transpose is fairly straightforward. So if you have a vector v and it's represented by this vector v, v1, v2, v3 with components or coordinates v1, v2, v3, then the transpose of this vector is equal to v1, v2, v3. In other words, the columns become the rows. And we use this kind of dagger. Mine just looks like a lowercase t, but your book looks like a fancy dagger. We use this little dagger notation for transpose. Next, we'll look at vector rotation. So we have a starting vector a, which we represent as the column vector a1, a2, and we're going to end up with a vector a prime, which we represent with the column vector a1 prime, a2 prime. And a1 prime, a2 prime is going to equal to the matrix with column vectors cosine theta, sine theta, minus sine theta, cosine theta, times our vector a, a1, a2. To see that this matrix here, which we will call r of phi, rotates our original vector a by an angle of phi, let's consider this drawing and also the fact, let's start with a1 prime is equal to this row here times this column. So in other words, a1 prime is equal to a1 cosine theta minus a2 sine theta. Looking at this drawing then, let's look at a1. So here's our vector a. So the x-coordinate for a here is going to be our a times cosine phi, and our y-coordinate here is going to be a sine of phi. So in other words, we're going to have, since a1, then our first coordinate, our x-coordinate is a cosine of phi, and a2, our y-coordinate is equal to a sine of phi, then our a1 prime is equal to a1, which is a cosine theta times cosine phi, minus a2, which is a sine of theta times sine of phi. Similarly, we have a2 prime is equal to a1 sine theta plus a2 cosine phi, I'm sorry, this was phi, a1 sine phi plus a2 cosine phi is equal to a cosine theta sine phi plus a sine theta cosine phi. Finally, using our trigonometric identities here, we can say a1 is a cosine theta plus phi, and again that's in the e1 direction, plus a sine of theta plus phi in the e2 direction. So that what we see is this then matrix here, rotates A, it adds another angle phi. So it rotates A by an angle of phi. And note, when we do the transpose over here, we're going to have to move this A1, A2 before the matrix, right? If you recall, if you have AB transpose, that's equal to B transpose A transpose. So now we've looked at this rotation matrix. Let's look at this in subscript notation. So A sub I prime, in other words, the A sub I row element, so it could be A1 prime or A2 prime, is equal to, well, think about if we get A1, we're multiplying the first row by the column. So we're holding the row, the first subscript constant, and it's the j that we're varying, and we're going to vary that with A sub j. So for example, when we did A1 prime, we wanted to hold this 1 constant, and it was the second because we're going across the row, so it's the columns that's incrementing as we go down this column here. So that's also incrementing. So this is our subscript notation to get the ith column of A prime. Another interesting note, now that we're in subscripts and we have R sub ij and A sub j, remember these R sub ij is just a number and A sub j is just a number. So now we can rearrange these. So R sub ij times aj is equal to A sub j R sub ij. Unlike matrix multiplication, order doesn't matter. By the time you have these indices, you're talking about the matrix elements. You're talking about real numbers, or it could be complex. You're talking about numbers, so you can, multiplication of numbers is commutative, so you can rearrange as you like. And just to be really explicit, I went ahead and I expanded A prime, A prime out. So that's R sub ij, aj, e to the I. Remember, that's the ith element. So here we have two indices because there are two dummy indices, so j and I. So we're going to sum over I, sum over j of R sub ij, aj, e to the I. So first I sum over j, I let j run from 1 to 2, and then I sum over I, and I get my final answer here, which you can see is the same as what we got here, right? Our A1 prime, so if I look at our A1, this is the terms for A2 because the E2, our first basis element, so this is the term for A1. So our A1 prime will be equal to R11, that's cosine theta times A1, that's here, plus our R12 times A2. So R12 is our minus sign of phi times A2. So that's this term here. You can see that our expansion agrees with when we did our matrix multiplication like we used to do in, vector calc. One other note, after subscript summation, the notation on the left-hand side must equal the notation on the right-hand side. So in the example above, the left-hand and right side both have no indices. So here we have no indice. And over here, we've summed over everything, so there's no indice. So you would never have something like A prime is not equal to R sub ij, aj, because the j's would be summed over, but then you would have this leftover indice I. So there's not an index on the left-hand side, so this would be invalid. So your indices on your equations have to balance. And that's kind of a little check to see that you've done everything correctly. So that was matrix multiplication. So that was a lot of detail in this one little line I dedicated to matrix multiplication. The next vector operation we will look at is the dot product, and here is the formula that you want to remember. A dot B is equal to A sub I, B sub j times this delta, Kronecker delta, ij, which is equal to A sub I, B sub I. So this is the formula you want to remember, but we're going to look at this formula and derivation in more detail on the next slide. And just a quick review of what we had learned about the dot product from vector calculus. So a vector A dotted with a vector B. So let's say it's a three-dimensional vector. So you have vector A, which is A1, A2, A3, and B, which is B1, B2, B3. You would multiply corresponding coordinates and then add them together. So that is A1 times B1 plus A2 times B2 plus A3 times B3. The other thing that you learned in vector calculus is the dot product is also equal to the magnitude of A times the magnitude of B times cosine of theta. So this was particularly useful when you wanted to know if two vectors were orthogonal, because if they were orthogonal, they would be at a 90-degree angle, meaning the cosine of 90 would be 0. So assuming A and B were not the zero vector, A dot B equals 0 would imply orthogonal vectors. Using the index notation, you will see A dot B is equal to A sub I, B sub j, this Kronecker delta ij, which is equal to A sub I, B sub I. And you can see, because then I becomes a dummy variable that we sum over, that is exactly equal to the dot product we had from vector calculus. But we will look at this index notation in a little more detail. One way to express this dot product, A dot B, in this index notation is written here. So A sub I, E sub I, that's the basis vector. B sub j, E sub j, that's the other basis vector. And for this example, we're going to assume we're in two dimensions, so I and j are going to run from 1 to 2. So if you look at this here, we're running I from 1 to 2 and the j from 1 to 2, meaning that it's not just A1 times B1 plus A2 times B2, it's all the combinations of i's and j's. So we'll also have A1 with B2. But that's fixed by these basis vectors here. So let's just take a look at this, a closer look at this. We'll write it out as the two summations. We have the I summation and the j summation. So we have A sub I e to the I and B sub j e to the j. When we run the j index from 1 to 2, so A sub I, E sub I stays, it has no j's, but the B sub j, E sub j becomes B1, E1, and B2, E2. Next, we can run the I summations, and that will affect the A components. So we have A1, E1, B1, E1, but we also need the A1, E1, B2, E2, and now when we increment I, we'll get the A2, E2, B1, E1, and A2, E2, B2, E1. So if you look at this point, we do have components of A1 mixed with B2. However, since E1 and E2 are a bases, that means our bases vectors are perpendicular to each other. So here, this will go to 0 because of the E1, E2, and this will go to 0 because of the E1 and E2. We are going to note in this expression, we kept the indice for A different from the indice from B. In other words, A had the I indice and B had the J indice, and that way they were independent, and we can get all the combinations of the A component with the J component. So we have A1, B1, A1, B2, A2, B1, and A2, B2. But this works out, again, because our bases were perpendicular. So A and B got two different indices, I and J, to keep the summations independent. We can simplify this dot product indice notation by using the Kronecker delta. And the Kronecker delta ends up being really useful later when we want to simplify other expressions as well. So the Kronecker delta, this is the delta ij, is defined as 1 when I equals j and 0 when I does not equal to j. In other words, this is the function that tells us when the indices are equal. Then, in this case, our dot product A dot B becomes A sub I, B sub j, this delta ij. If I want to expand this expression out, then A dot B is equal to A sub I, B sub I, D sub ij. So now because I is a dummy variable, it appears twice, and j is also a dummy variable, it appears twice. So both I and j are summed over. So I'm going to sum over I and sum over j. And I and j both sum, we're in two dimensions, I equals 1 to 2 and j equals 1 to 2. Then we have A sub I, B sub j, delta ij. So I'm going to start with summing over j. So my i's out here, I have a sub I, then b and this delta have j terms, so I'm going to get b1 and delta I1, and then when j is equal to 2, I have my a sub I again, my b sub 2, delta I2. Now, next, I need to sum over my I, and I'm going to get, when I equals 1, a1, b1, d1, 1, plus a1, b2, d1, 2, and then when I equals 2, I have a2, b1, d2, 1, plus a2, b2, d2, 2. And looking at the definition of my Kronecker delta, it's equal to 1 when I is equal to j, and 0 when I does not equal to j. So this first one here, this goes to 1. This here goes to 0 because I and j are not equal. Here I is equal to 2, j is equal to 1, so this goes to 0. And here I and j are both equal to 2, so this goes to 1. Which leaves me with a1, b1 plus a2, b2, which is exactly my dot product for a two-dimensional vector. And one of the nice things about a Kronecker delta that lets us simplify expressions, as in these examples here, so anytime a Kronecker delta exists in a term, with one of its subscripts repeated somewhere else in the same term, the Kronecker delta can be removed, and every instance of the repeated subscript changes to the other subscript of the Kronecker delta. So for example, here we have a sub I, this delta ij. So we see that one of the subscripts is repeated, that's the I. So the Kronecker delta can be removed, so we removed it over here, and every instance of the repeated subscript, that's I, is changed to the other subscript of the Kronecker delta, so that means this I then is changed to j. So a sub I delta ij is equal to a sub j. Here's another example. We have ai b sub j delta ij. So here we have j appearing is repeated. So we can remove the Kronecker delta, and then we give our b now the I index. So we have ai bi. So now we sum over the I here. Here we have a matrix element, the ith jth element of a matrix, times ak times our delta ik. Here again, k is repeated, and so we can get rid of the Kronecker delta, and then the a takes the subscript I. So we have m sub ij times ai. So now we're summing over the ith index here. Finally, here we have b sub I, t sub jk, e to the m, this is the mth basis vector, this delta jm. Here we have the repeated symbol m, so e, our basis vector, then becomes e to the j, and everything else remains the same, b sub I, t, jk, and e to the j. And here we're summing over the jth element. We have this other note. Flexibility is one of the things that makes calculations performed with subscript summation notation easier than working with the matrix notation. So these properties here would have been more cumbersome if we had to work with an entire matrix and do matrix multiplications. For each term, it would have been a lot of work. Whereas here, once you get used to it, simplifying with these indices can be much faster. The last note we have for the Kronecker delta is it can also be viewed as a matrix or matrix array. So this Kronecker delta ij is equal to the matrix 1, which is defined to be the identity matrix here. And if we're in 3 dimensions, it's this 3-dimensional identity matrix. So then a dot b becomes a sub I, b sub j, the Kronecker delta ij. We've already determined that from here. But this d sub ij can be considered a matrix. So now we're going to have a transpose 1, the identity matrix, times the matrix b. So it looks like this here, which is equal to a transpose b. Remember, this is the symbol, this dagger symbol, which just looks like a T when I write it, is our transpose. And so note, this is the dot product definition. We can use this one, we can use this one, or we can use this matrix form for our dot product definition. So in our overview sheet, we just talked about dot products. We said we have this form of our dot product, and we could also put in the Kronecker Delta, and then our matrix form of the dot product, which is actually kind of interesting. So A dot B is just A transpose times B. So the next topic we're going to cover is the cross product and the Levi-Cevita. To review the cross product from vector calc, when we crossed a vector A with a vector B, it was the determinant of the ijk vectors with the A1, A2, A3 components, B1, B2, B3 components. And to get the determinant of a 3 by 3, we started with this first I component here, would get moved here, and then we would cross out the row and column that the ith component was at and take the determinant of what was remaining. So the 2 by 2 would be A2, A3, B2, B3. Next, we'd go across the row and expand with the J component, and then we would cross out the row and column that J was in and take the determinant of the remaining 2 by 2. That would be A1, A3, B1, B3. Finally, we would consider this K. We would expand across the row K, cross out the row and column that K comes from, and take the determinant of the remaining 2 by 2, which is A1, A2, B1, B2. And then to get the determinant of the 2 by 2, we just cross multiply. So it's A2, B3, and then a minus. A3, B2. Also in the determinant, we alternate the sign, so this is minus, and then we have A1 times B3, that should be 3, minus A3, B1 in the J direction. Let me correct this, this should be B3. And then over here we have A1 times B2 minus A2 times B1 in the K direction. This resulting vector, right, we have an I, J, and K component of this three-dimensional vector, ends up being a vector that's perpendicular to both A and B. And we have this right-hand rule. So if this is vector A and this is vector B, and we're doing the cross product of A to B, we curl our fingers from A to B, and our thumb will point in the direction of A cross B. And it's either going to point up or it's going to point down. So the idea is A and B are in the same plane, and then our A cross B is perpendicular. And there are two ways to be perpendicular to this plane that A and B are in. It's either going to be up or down. And then I just copied this formula over here for your reference, and instead of the I, J, and K as our basis vector, I went ahead and used E1, E2, and E3 because that's the basis vector. That's how it's notated in this book. The other thing is I have a plus here because I reversed these two terms. You may notice I already put this third way of expressing this, which is A sub I, B sub j, e to the k hat, and then this epsilon ijk, where this epsilon ijk is the Levi-Cevita symbol, and it's equal to 1 for ijk being even permutations of 1, 2, 3, negative 1 if it's an odd permutation of 1, 2, 3, and 0 if two or more subscripts are equal. And what is meant by an even or odd permutation? Well, an odd permutation of 1, 2, 3 is any rearrangement of these three numbers that can be accomplished with an odd number of pair interchanges. Thus, the odd permutations of 1, 2, 3 are 2, 1, 3, 1, 3, 2, and 3, 2, 1. And to illustrate this last one, 3, 2, 1, why it is an odd permutation of 1, 2, 3, we start with 1, 2, 3, and then we want to keep interchanging two neighboring pairs of numbers until eventually we get to 3, 2, 1. And the way I chose to do that is first I interchanged 1 and 2. So then I get 2, if I change the positions of 2 and 1 or 1 and 2, I get 2, 1, 3. Then next I interchanged the 1 and 3 so that I got, well, I still have my 2 and my 1 and 3 changes position. And then finally, I changed the position of 2 and 3, and I get 3, 2, 1. You may do your interchanges in different orders, or you may have extra interchanges, but to get from 3, 2, 1, from 1, 2, 3 to 3, 2, 1, you're always going to have an odd number of interchanges. I had 1 interchange, 2 interchange, and 3 interchanges. So that's an odd permutation. An even permutation, on the other hand, the even permutations of 1, 2, 3 are 1, 2, 3, 2, 3, 1, and 3, 1, 2. To see that 3, 1, 2 is an even permutation of 1, 2, 3, we start with 1, 2, 3, and then what I did is I interchanged 2 and 3 to get, well, our 1 stays, and then 3 and 2 changes places, and then finally I changed the places of 1 and 3, so I get 3, 1, 2. So I took 2 interchanges, so it's an even permutation. And again, you could have done these in different order. You could have had another 2 interchanges, but whenever you go from 3, 1, 2, 1, 2, 3 to 3, 1, 2, it's always going to be an even number of permutations. I am not going to expand this out to show that it is equal to this expression here. I'll let you do that if you'd like. But this here, this expression is the one you want to use for A cross B when you're trying to do proofs or simplify things. There are 2 properties of the Levi-Cevita that's really useful. The first one is if you have 2 Levi-Cevita symbols next to each other with the same last subscript. So it doesn't work if this is epsilon ij k epsilon lmn, but if the last subscript matches this one, so if it's k and k, then that's equal to this Kronecker delta, delta il, delta jm minus delta im, delta jl. So in other words, it's delta the first and the first symbol, delta the second and the second symbol, minus the first and the second, times the second and the first. So this is good if you ever need to somehow relate your Levi-Cevita to the Kronecker delta. And the other property of the Levi-Cevita is reversing any 2 of the subscripts just changes the sign. So here we reverse the I and j and it changes the sign. Here we reverse the I and j again and we change the sign. And here are the Levi-Cevita notes at the bottom of our overview slide with the 2 properties named over here. Next, we'll do a couple of examples. And for my examples, I put a very brief summary of some of the things I thought were important up here, but really you want the whole page, the overview slide. It's just that if I put the overview slide here, there'd be no room for anything else. The first example is to consider 2 products, this A dot A and A prime dot A prime, where A prime is generated by rotating A counterclockwise by an angle theta. First, we want to do this product using matrix notation, and then we want to express it using the subscript summation notation. I start by writing A prime in terms of A. So first, A prime can be represented by our matrix A prime, which has components A1 prime, A2 prime. And we had covered this earlier when we were talking about vector operations. One of the first ones we talked about was rotation. And so a rotation by an angle of phi is equal to this matrix here, which we called R of phi, which is cosine phi minus sine phi, cosine phi, times our matrix A, or our vector A. So it is expressed here as a matrix multiplication. Next, if I want to express the dot product of A prime dot A prime, I am going to use this definition, where is this, of my dot product over here. So the dot product of 2 matrices I can express as the first matrix transposed times the second matrix. So I take my A prime, this first matrix transposed times the second matrix. And from linear algebra or any other class you had worked with matrices, you want to recall that A times B, a matrix A times a matrix B transpose is equal to B transpose times A transpose. So these have to reverse. So here, for my R times A transpose, that's equal to A transpose R transpose times R A. And then a matrix times its own transpose gives us the identity matrix. So what we're left with is A transpose times A, which is equal to our A dot A. So I actually did both of these at the same time. So A prime dot A prime will equal to A dot A. Next, I want to consider subscript and summation notation. First, I have my A prime, which is equal to R times A. And then in my matrix multiplication notation, that means that A sub I prime is equal to R sub ij times aj. Remember, these j's kind of cancel out the same way they did over here. So A sub I prime is equal to R sub ij, A sub j. Now to get my A prime dot A prime in summation notation, so I'm going to look at my dot product summation notation. Here's my dot product. I'm going to use this summation notation here because I'm not doing the matrix multiplication. So that's going to be equal to my A prime some index R, my A prime some index X, delta S, delta RS. So compare this here, what I've written here, to what I've circled here. And one thing you want to note is I didn't want to use my I and J index here because my I and J index are on A. So I wanted different indices, so I chose R and S to be different. And next, because of our Kronecker Delta here, my S is repeated. So what I can do is I can get rid of the Kronecker Delta, but I need to replace this index with the other index in my Kronecker Delta. So now I have AR prime, and this here becomes AR prime as well. If you wanted, you could have changed this into S, right? You could have combined this AR with this DRS, and that would give you the same results later. But I just chose to combine this A prime with this delta ARS. Next, instead of the A prime, we're going to look at the relation between A prime and A. And so we can substitute A in there. So what we're going to get is AR prime. We're going to use this as ARJ times AJ. And then for this one, because we're multiplying, we need to run a different index. So we'll have ARK times AK. And again, now we're not multiplying matrices, but we're multiplying elements of the matrix, so we can rearrange. So we can put the A's together, AJ, AK, and the R, RJ, and RRK. Looking at this multiplication here, when we had our matrix multiplication and we had the second index and the first index here, we can contract over and get the P sub IK. Here it doesn't really work because we're contracting over the first index of both matrices. So this, to make sense of it, we're going to put the transpose here. So we're going to have AJ, AK, R sub RJ transpose, R sub RK. So now we have, since this is just a transpose times itself, that's the identity matrix. So what we get is AJ times AJ, which is equal to A dot A. And we can see this is exactly what we got with the matrix notation. The next example is derivation of identity for the double cross product between three vectors, that is A cross B cross C. I'm going to start with B cross C. I'm going to set that equal to D. So B cross C, using our definition of cross product over here, is going to be B sub I, C sub J, E K, and the Levi-Cevita IJK. Now when we take A cross B cross C, that's A cross D. And we're going to use different indices because they need to be independent. So we're going to have AR, so we're using R, S, and T instead of IJK. So we'll have AR, DS, E to the T, the Levi-Cevita RST. Now looking at this DS, so because bases are perpendicular, the S, the component of D, is obtained by multiplying D times the basis E to the S, right? Because all the other components, since they're, if here our basis in the RST, R is perpendicular to S and T is perpendicular to S, so all the other components of D will go to 0 when you multiply by E to the S. So E to the S, and then using this here for D, B sub I, C sub J, E to the K, epsilon I, J, K. And now, while matrix multiplication is not commutative, these are components of matrices, so they're just numbers. So we can rearrange them. So we can have the B sub I, C sub j, our epsilon I, j, k, and then we can group these two epsilons together, ES, EK. And ES, EK, again, they're perpendicular unless they're the same and then they're equal to 1. So that gives us the delta Kronecker of SK. And then according to our properties of the Kronecker delta, when we have this indice k repeated, we can get rid of the Kronecker delta, but then we must replace this k with this s. So we have B sub I, C sub j, E sub I, j, s. So now for A, B, C, we have our A sub r. And then for D of s, we have that here. B sub I, C sub j, epsilon I, j, s. We have our E of t and our epsilon of r, s, t. So what this is going to be equal to is A sub r, B sub I, C sub j. We have our epsilon of t, our epsilon of I, j, s, and our epsilon of r, s, t. The next thing we want to do is simplify these two epsilons. And the thing is, we have this rule here that we can use if the last index is the same, which they are not here, but we can switch the order of indices around, just making sure that whenever we switch interchange to, we're going to put in a negative sign. So for this, we're going to keep this as RJS, but we want to switch these indices around so S is at the end. So when we switch the S and the T, we need to introduce a negation sign. So this is the negative, and then, which comes over here. And then now we have the common indice, so we can use this property here. So epsilon ijk, epsilon lmk, again, same indice at the end, is the delta il, delta jm. That's delta the first times the first, delta jm, that's the second times the second, and then minus delta im, delta jl. That's the first times the second, here's the second, and the second times the first. So here we're going to use that property. We've switched these around. So this stays the same. We have our negative sign. We're going to have the first times the first, that's delta ri. The second times the second, that's t times j, delta tj, minus, now we're going to have the first times the second, which is r and j, and then the second times the first, which is t and I. From here to here, all I did is I put in the negative sign and moved the terms around. So this becomes positive and it's minus this term here. And then this next step, I started to multiply. Again, these are just numbers now, right? They're components of vectors, and so I can just move things around. I'm going to multiply this first times this first product of the Kronecker deltas, and I'm going to put the drj next to the ar because I'm going to simplify this later. So ar drj, b sub I, c sub j, et, and then I still have the delta ti. Now multiplying this delta Kronecker product times this factor here, I'm going to have my AR, I'm going to put my delta RI, my BI, my CJ, my ET, and then I'm going to have my delta TJ. Now here, because it's a Kronecker delta, I can reduce, so I can get rid of the Kronecker delta, but this index needs to become J, so I have AJ, BI, CJ, EI. Similarly, over here, I can get rid of the delta Kronecker, and then the index here needs to become I, AI, BI, CJ, EJ. Again, these are just numbers now, and I can move them around, so I can group my A sub j with my C sub j, and my BI with my EI. Similarly, over here, I can group my AI and BI, and my CJ and EJ. So here, this A sub j, C sub j, is exactly the definition of the dot product. So this is A dot C, and here we have the definition of our matrix multiplication. So that's B, and then minus A dot B times C. And in case you're wondering, when I went from this step to this step, I grouped the Kronecker Delta D, the delta Rj with the AR, but I could have grouped it differently. I could have grouped it with the C sub j, and you'll still see the same result. So I'll do a little bit different grouping over here of these factors, and you'll see the results the same. So I got rid of some calculations, and I moved this portion here that I wanted to compare up to give myself some more space. Now, again, what I wanted to do, instead of grouping this delta Rj with this R, I'm going to group the delta Rj with the C. And then similarly, over here, instead of grouping the delta Ri with the AR, I'm going to group the delta Ri with the B. So this grouping of the C with the delta Rj, again, we can get rid of the Kronecker delta, but we need to replace this J with an R. So I have AR, BI, CREI. Over here, when I group this delta close to the B sub I can get rid of the Kronecker delta, but I need to replace this index with R. So I have AR, BR, CTET. Now again, I can rearrange, so I have my ARCR, BI, EI, minus ARBR, CTET, and this is exactly A dot C times B minus A dot R times C, which is exactly what we had gotten previously. Now that we covered the material for this video, I have 3 more problems for you to try for review. And what I'm going to suggest at the end of each problem statement that you pause the video, give the problem a try for yourself before you take a look at the solution, which I will provide for you with a few explanations around key points. The first problem is to reduce the delta Ij, delta Jk, delta Ki. I rewrote the problem delta Ij, delta Jk, and delta Ki. So I grouped the first 2 together. So I have delta Ij, delta Jk grouped together, and then delta Ki. Since these 2 have a common index, we can get rid of that, and we're left with delta Ik times delta Ki. These 2 also have the common index, so we're left with delta II. And one thing we want to remember is now that we have a delta II, this repeated index here does imply a summation, so we're going to sum over the variable I. And also, just to remind you, delta Ij is equal to 1 when I equals j, and 0 when I does not equal to j. So delta II, summing over I, assuming this is a 3-dimensional space, is going to be equal to, when I is equal to 1, we have delta 1, 1, which is equal to 1. When I is equal to 2, we'll have delta 2, 2, which is equal to 1. And when I is equal to 3, we'll have delta 3, 3, which is equal to 1. So our delta II will equal to 3. And 3 is our final answer. For this next example, I went back to this notation where vectors are lowercase because the r is supposed to suggest radius. So if we have our radius vector equal to x sub I, e sub I, and again, this is an implied summation, we want to find the notation for our hat, where our hat is equal to the vector over the magnitude of the vector. So first, the magnitude of our vector r is equal to the square root of x1 squared plus x2 squared plus x3 squared over here, which is the summation of x sub I sub x sub I raised to the 1/2. And we can get rid of this summation because we have this double index, x sub I 1/2. So that means our hat is equal to x sub I e sub I hat over x sub j raised to the 1/2. And notice here, you do want to have I and j summed independently. To see why, if we didn't do them independently and when we used both the top and the bottom term the same index, you see that that would equal to, when I equals 1, we'd get x1 e1 over x1 squared plus, and then for I equals 2, x2 over e2 times e2 over x2 squared plus, when I equals 3, x3 e3 over x3 squared, which is not equal to r. You can see when we keep the indices separate, so x sub I, e sub I, xj to the 1/2, so we can sum over I first. So we're just going to pull out this x sub I term, and we're going to sum over j. So we have 1 over, when we first get j equals 1, we're going to have x1 squared and then x2 squared and x3 squared, all square rooted. And then when we sum over I, we're going to get the x1 e1 plus x2 e2 plus x3 e3 times this constant over here. So you can see that this is equal to r. So many times when I've said that we need to keep the indices separate, you can kind of test it out if you're not sure. This next example is sort of similar to one we had done, example 2, in the previous slide, but we want to prove now that the vector A cross B cross C is equal to A dot C times B minus A dot B times C. So this first part here I got directly from our previous example. So please take a look, because this is not actually just one single step. There's a couple of things going on in here, in particular how we simplified the e to the ijk and e to the k with the e to the t. So this kind of got simplified down. So do take a look. But once we get to this point, then I can regroup or rearrange. So I have my AR, BI, CJ, and now I have my epsilon of T, my epsilon of RST, and epsilon of IJS. Again, we want to use this formula here to kind of simplify our epsilon, our Levi-Cevita. But first, we need to have the same last index, which we do not, which means we need to rearrange. So we can rearrange, but we need to introduce the negative sign. And then after that, we use this property here to get, to replace these epsilons with deltas. And one thing I wanted to mention, one, I did use this property because it does simplify things, but also at the time I was thinking this Kronecker Delta would come in handy because that's my dot product. But anyway, things did simplify down, and you can look at the calculations, and I do end up with this, the desired result here. So that's it for this video. It did end up being much longer than I wanted, so I'll be careful in future chapters to go make a video per section, or maybe 2 sections, not try to cover a whole chapter at the same time. I was misled because I thought since it was just a review and maybe some new notation, it would be much faster, but it wasn't. So I do apologize for that. But I will say that's it for this video. Thank you for watching.